Our next topic is what we call the linear combination of atomic orbitals, or LCAO. And the basic idea here is that we already know what electrons want to do when they're near an atomic nucleus. And within a molecule, most of the space is actually really close to one nucleus or another. And so a good starting point for figuring out what the wave functions of the electrons look like in a molecule is going to be the wave functions those electrons have for atoms alone. And in fact, many of the orbitals in molecules will be very, very close to those atomic orbitals, and others will be a little bit more modified. And so what we're going to do here is stick to diatomic molecules. In fact, so far we're actually technically sticking to what we call homonuclear diatomic molecules. So we have two identical nuclei. Let's put a couple down here. They're positively charged. And now what I'm going to do is copy this set and look at a whole number of them, and we're going to have some sort of general energy type relationship as we're going up here in the space, though I'm not really being explicit about that yet. So we've got these two nuclei repeated many times, and now we want to consider what happens as we take various atomic orbitals. And so far we're just dealing with one electron. These are what we call single electron orbitals. Just like we did with the atom, we figured out what the orbitals would look like for a single electron in an atom. And then the overall Hamiltonian, the overall energy, included an electron-electron interaction term, H prime as we called it in our perturbation theory back in Unit 3, but the first order assumption was that the wave function itself, the orbital itself, didn't change physically in space all that much. So we're just going to deal with single electrons at the moment. And we're going to start basically with a 1s orbital. And so the first option we have is to take two 1s orbitals and just add them together, right? So these two little hats here in the same phase, and we're going to call this sigma, specifically sigma 1s. And that's just the 1s orbital of A, which is the left-hand nucleus, plus the 1s orbital of B, with an appropriate bit of normalization in there that we're not going to worry about yet. So the next option is to just add them in the opposite way. So if we have the orbital for nucleus B pointing downward, that's 1sa minus 1sb, and we're going to call that guy sigma star. You probably already know what that means, but we're going to get to that in a little bit. So then we can do the same thing for the 2s orbital. Then we don't even worry about it. For the 2p orbital, it's a little more interesting. So if the orbitals are aligned along the axis connecting the two nuclei, which is the bonds, that's the z-axis. And so that's a pz orbital. So if I have the 2pz orbital for A, for the left-hand nucleus, minus the 2pz orbital for B, so the different p orbitals have the opposite signs, then I get this positive overlap in red between them. And that's another configuration that is sort of lower in energy because it's going to have basically two nodes, where those p orbitals individually have nodes near the nucleus, but it's going to have a large blob of one sign in the bonding area between the two nuclei. And for both the sigma 1s and this what we call sigma 2pz orbitals, in both those situations we get a lot of electron density between the two nuclei, and that indeed is what we're used to thinking of as a bonding interaction. And specifically we're used to thinking that as a sigma bond. So you've learned that nomen, that designation of this as a sigma type bond, where the electron density is located on axis right between the two nuclei. And we're going to see now why that matters. Now the other option I have with the p orbitals is of course to have them aligned perpendicular to that bond, and that's px or py. And I put these guys up, and if the phase is properly matched, then that we could call pi 2pxy, or really 2p plus or minus, and that comes from taking the 2p xy orbital in A, and now with the same sign adding in the 2p orbital in B. And once again, this has got overlap, positive overlap between the two nuclei on each side of the of the bond, if you will. But now there's rather than having the overlap be right on axis between the along the bond radius along the z-axis, it's displaced off in space parallel to that axis, and that's what we know as a pi bond. But again, we're now working on why that thing is called a pi bond. And of course, the next option I have is to anti-align those p, x, or y orbitals and put them out of phase, but we won't even worry about that now. And of course, I can anti-align the pz's as well and get a sigma star. So there's a pi star and a sigma star that are pretty straightforward up there. So the question is, we've always known these are sigmas and pi's, but the issue is, why do we actually call them that, and where do the names come from? So let's look at that nomenclature now. So the nomenclature for molecular orbitals is, again, pretty straightforward. So we got the z-axis here. This is the bond axis. So here's our two nuclei. And the big deal here is the amount of orbital angular momentum around that bond axis. So this is Slinky again. So this is basically Slinky's last stand, or last gasp in this class. And so what we're going to keep track of now is not the total angular momentum around an individual nucleus, because that's not quite so useful anymore. Now we have this very strong orientation within the molecule, which is the z-axis that defines the bond. And so what we would call the good quantum number here becomes m sub z. It becomes the amount of angular momentum around that z-axis. And so if I have an s orbital, of course m sub z is 0, because there's no orbital angular momentum of any kind. So any s orbital is automatically going to have m sub z equal to 0. But the p orbitals are a little more interesting. But so the s orbitals are automatically going to be called sigma, because for the m sub z, we're going to in the molecular orbital case, instead of using SPDF, you're going to see in a second, we're going to use sigma, pi, delta, etc. And so the s orbitals have no m sub z equal to 0, and so they're automatically going to be this sort of sigma style thing. Pz, however, also has m sub z equal to 0, right? If the molecule is along the z, if the electron is along the z-axis, remember the polar orbits we were talking about earlier when we were defining the orbital angular momentum around an atom. That means that in order to have a high probability of being found along the z-axis, there has to be no component of angular momentum about that z-axis. So the pz orbital has no z angular momentum. That's what we learned in Unit 3. And so interactions of pz orbitals also are of sigma character, because sigma designates the orbital angular momentum about the z-axis. And it's the pxy, or the p plus and minus, that have the m sub z of plus or minus 1, and those we designate as pi, because that's the deal. If we have atomic orbitals that are sp, d, f, g, etc., the molecular orbitals are going to be sigma, pi, delta, phi, gamma, but beyond sigma, pi, delta, actually, we've basically never encountered the orbitals, so we're not going to have to worry about the higher order names for these things. Okay, so let's actually start making these orbitals and ranking them and looking at what they do for energy. And so these are what we call molecular orbital correlation diagrams, because what we're going to look at is now, remember, as we looked at H2 forming and we thought about the lowest electronic state of the system, we considered the fact that we started at infinite separation with an electron in essentially around one of the atoms, and then we started to draw closer together, and we separated via the Born-Oppenheimer approximation what would happen to electronic energy from what would happen with a nuclear repulsion. So here we're going to think only about the electronic energy. That's really important. This is what happens to the electronic energy as you draw these nuclei closer together, or force them to be closer and closer together, but within the Born-Oppenheimer approximation, we're basically pinning the nuclei at a given point in space and asking what happens to the electronic energies here. So here's some nuclei A and B, and we start with a 1s orbital about A, and then there's a 2s orbital that's much higher in energy, of course, and then the 2p orbitals as single electrons. Those are going to be actually the same energy as the 2s, but we know as we get to multiple electrons, those are going to be higher in energy, and even in the molecular orbital interactions to make single electron orbitals, they're somewhat higher in energy. So we use the standard ranking here of 1s, 2s, and 2p orbitals in that order. And of course, B is identical. Oh yeah, the m sub z around those is again important. So the middle is 0, the left is -1, the right is +1. So that's the m sub z component. That's all important as we define these molecular orbitals. And then B's got the same set. So we've got these two sets of atomic orbitals, and we're bringing the atoms closer and closer and closer together. So just as we saw before with the H2 ground state, as we bring the system closer and closer together, the first thing that happens, the only thing we cared about for H2 was this interaction of the 1s orbitals. And so 1s, when we have the sigma bonding interaction of the two orbitals having the same sign with each other, then we discovered that the electronic energy started to go down. And remember, it would go down ultimately quite a lot if we could bring the nuclei all the way together. We'd go from -1 Rydberg to -4 Rydbergs. And so that's a stabilization associated with what we call atomic overlap. As we build up this molecular orbital, the wave function gets more extended, the wavelength gets longer, which means the kinetic energy goes down. That stabilization is lowering the energy. The other option was to have the orbitals have opposite signs and make a sigma star 1s orbital, as we defined earlier. And there, the fact that the two are interacting with each other is actually making the curvature go up. We've got this node in between A and B, and so the overall curvature in the wave function will be larger than it was before, and so the energy will rise. And a basic rule here is the splitting is very, very close to symmetrical. In other words, the increase in energy for the sigma star relative to the separated 1s orbitals is just about the same as the decrease in energy associated with the sigma. And so they split fairly symmetrically. To what's called second order, the destabilization is basically always a little bit higher than the stabilization. So actually the 1s, the sigma, doesn't go down quite as much as the sigma star goes up. But that's a little detail that doesn't matter too much at this point. So then the same thing plays out for the 2s. Basically, it's identical. So there's a sigma and a sigma star 2s that look exactly the same. The interesting thing goes on with the 2p. For single electrons, the most stabilizing interaction is going to be the 2p Z interaction, which is going to make a sigma bond. And so the 2pz sigma bonds are going to be quite significantly split because the 2p orbitals have a lot of overlap there, and we get the sigma and sigma star 2p's. And remember, the sigma 2p actually has opposite signs for those 2p, so it's 2pa minus 2pb to get the sigma type positive overlap between the two nuclei. And the sigma star is the other sense, so the sigma star has 2p A plus 2p B, getting the negative overlap. And then there's the pi-type interactions. And so those we draw off to the side here because they have m sub z plus or minus 1. They have slinky going on, and they have, for single electrons, typically a little less splitting, and this is pi 2p and pi star 2p. So we draw them from the 2p orbitals, and we get that. And so this basic set of orbitals and the splitting is what we call a correlation diagram. And that's the way the orbitals set up, and the nomenclature sets up for homonuclear diatomic molecules, so identical nuclei, and we run the molecules up, the molecular orbitals up this chain, and very soon then we're going to start filling those things up. Let's just review again what these look like. So the 1s looks like that, and the sigma 1s orbitals look like this. The sigma bonding 1s is what we call gerade, symmetry again, remember, because if I do the reflection symmetry, I get the same sign, whereas for the sigma star, I get an ungerade symmetry, so I can put that superscript G and superscript U to designate that. The two S's are identical. Same. There's a node in there near the nucleus that I haven't drawn, but in the large scale, it's exactly the same. And then we go to the p orbital overlap. The first one is the sigma type. So those guys look like this. And once again, the sigma bonding orbital has Gerada symmetry, so we reflect about the z-axis and the internuclear plane of symmetry, and we get the same sign no matter what we do. Whereas the sigma star 2p again has ungerade symmetry. So for all the sigma orbitals, the bonding orbital is going to have a Gerada symmetry, and the anti-bonding star orbital is going to have an ungerade symmetry. When we look at the pi orbitals, the story is a little different. So now the pi bonding interaction actually has the ungerade symmetry, because the lobes of the pi bond have opposite sign as I reflect through that axis of symmetry, whereas the pi star actually has the same sign reflecting through that axis of symmetry. And so the pi bonding orbital is ungerade, and the pi star has the Gerada symmetry. It's really important to realize that these interactions that we typically draw in a molecular orbital correlation diagram are for the electrons only. So if we put the whole system together, here are our two nuclei, Pauli and Born, right? And typically at some happy distance with each other, where we're basically going to make a sigma bond, and we've got a couple s orbitals that we're going to correlate with each other, but we've brought the nuclei together. So from the nuclear perspective, there's already a significant penalty to be paid, which is the nuclear repulsion term, right? So the overall energy, you can think maybe about paying that first. As we draw these nuclei together, they're just grumbling, they're angry, so we're uphill. But we're forcing them to do that, to just figure out what the electrons are going to do about the situation. And in this happy situation, the electronic stabilization looks like this. And so there's our sigma and our sigma star bonds. And the electronic energy, the negative attractive electronic energy there of the electrons being attracted to the two nuclei close to each other, exceeds that nuclear repulsion penalty. And so that overall sigma bond is stabilized with respect to the two nuclei at infinite separation. The sigma is below that infinite separation point there, and we have ourselves a bonding situation, and I've got an orbital that I can shove a couple of electrons into and get a beneficial situation here. The sigma star, on the other hand, actually raises the energy, and so even with respect to just the electronic situation, it's a net loss compared to having the nuclei infinitely separated. So the electrons themselves pay a penalty. I increase the curvature of the electronic wave function with respect to the 1s orbital or any s orbital by distorting it. And essentially, you can think of it as I'm generating some, I'm forcing some polarization on the one of the atoms with the other charge, and that polarized system has a less than optimal electronic distribution, and so the energy goes up. And so the sigma star is not only anti-bonding, it's anti-bonding with respect to the electrons, and the energy goes up from the nuclear repulsion as well. So it's a bad deal. Now if I bring the nuclei really close together, and we put them together like this, now that nuclear, so here's our 1s orbitals, the nuclear repulsion term is enormous. And so there's the infinite separation. So in this situation, remember that ultimately the electrons could get 3 Rydbergs of stabilization out of the deal. An electron could, to try to make a helium. So actually the electronic stabilization goes way up in this situation, but it's no longer beating out the nuclear repulsion term. And so the situation is net non-bonding. It's net repulsive at that point, and I'm in the part of the potential energy curve that we call the nuclear repulsion or the repulsive wall. So we look at the electronic part of the deal, but we always have to remember that the nuclear repulsion term is in here as well. So that basically does it for the single electron molecular orbitals. We know how to construct them, we know what makes their energy the way they are, and then we can turn our attention to adding multiple electrons into these things in the next section.